you know that in control systems we use feedback. What is the advantage of feedback? Feedback can overcome any external disturbances. However, there is one disadvantage of feedback. Feedback may result into instability. What is stability and instability? That we shall discuss in this lecture. So there are basically different definitions of stability. The definition which we shall be using in this course is called bounded input, bounded output stability. That is, a system will be BIBO stable if you apply a bounded input to a system and in response to that there is bounded output, right? For example, if you apply an input to this system, the input, for example, is step input. This input, magnitude of input is bounded, and in response to that the output grows unbounded with the time, then this system will be unstable. So without finding the solution to differential equations, how we can determine stability of systems? We can easily determine the stability of a system by looking at the location of poles. So how we do that? You remember, if you for example have this system 1 over s plus 2 and let's take 1 over s minus 2, and you apply an input r of s, the output is c of s. You remember that for a step input, the output, Laplace transform of output is given by this relation, and to bring it into time domain we take inverse Laplace transform. For that purpose we make partial fraction expansion. So partial fraction expansion is some constant over s plus another constant over s minus 2, and therefore in time domain you see that it is equal to a plus b e raised to the power 2t. The poles of this system can be plotted in S plane. There is one pole located at s equal to plus 2. So you can see that this pole appears as an exponent over here. This is growing exponential. That is, if pole of a system is in the right half S plane, the response will become unbounded. If the poles are in the left half S plane, the response will be bounded. So a necessary and sufficient condition for stability of a system is that poles of that system must be in the left half S plane, or real part of poles of a system, if these are less than 0, then the system is stable, right? Real part of a pole is less than 0, then this system is stable. We have taken this for the case of a first order system. That is true for any system of any complexity. For example, if we take a general system with the nth order, then we have a general transfer function with the nth, it is an nth order system. Its step response c of s. What is c of s? C of s is obtained by multiplying this transfer function with the Laplace transform of input. If we have unit step input, its Laplace transform is 1 over s, and therefore c of s is equal to this multiplied by s. And to bring it into time domain, what you do is you make partial fraction expansion. How do you obtain partial fraction expansion? What is strategy? If this polynomial, you can compute the roots of this polynomial. These polynomials, yes, you factorize it. So this polynomial can have real roots as well as complex roots. So let's write it in this form. That is, this polynomial this polynomial can have real roots as well as complex roots. For real roots, the partial fraction expansion. For complex roots written together, and here you already know this, how did we achieve it. And then after partial fraction expansion, what will be the inverse Laplace transform? A. So inverse Laplace transform of this expression is like this one. When the poles are in the right half plane, then this exponential term will grow. Likewise, this exponential term, which was this exponent which appears over here, was real part of these complex roots. So if this term grows or this term grows, the response, total response will grow. So conclusion is that if any of the pole is in the right half S-plane, the system will become unstable, right? If you are feeling difficulty with this complex expression, so let's take some example to demonstrate these concepts. We have this control system and we want to see the stability of this system. There is, if we apply bounded input to this system, what will be output, whether bounded or unbounded? For that purpose, first step is to obtain the closed loop transfer function. Forward transfer function, that is 3 over s plus 1 into s plus 2 divided by 1 plus this forward transfer function, because there is unity, it is unity feedback. So what is location of poles for this transfer function? Location of poles, this is the same as, so what is location of poles for this system? You can find the roots, and those roots can be determined by, for example, your calculator, and these come out to be at this location. All the poles of this system are in the left half S-plane, therefore the system is stable. So as a conclusion, if all poles of a system are in the left half S-plane, the system will be stable. If any of the poles are in the right half S-plane, the system will be unstable. There is a case which when the poles are pure on the imaginary axis, then we call that system as marginally stable or critically stable. That is, that system is at the verge of stability. There is one difficulty over here. Difficulty is finding the roots of these polynomials. Here it was third order polynomial, and still you had to put some effort to compute the roots of that polynomial. To avoid that difficulty, there is a criteria. You have already studied that criteria, so we shall quickly go through that thing, which is called Ruth's Hurwitz stability criterion.